Welcome to the lecture 6 in this lecture series on noise control in mechanical systems. I am Professor Sneha Singh from the Department of Mechanical and Industrial Engineering at IIT Roorkee. So, this is the lecture 6 whose title is Intensity and Power. So, here we will be discussing two important terminologies with respect to sound wave propagation, that is the sound intensity and sound power. So, to quickly sum up the summary of the previous two lectures, we studied about the harmonic plane wave and we found the solution for a harmonic plane wave using the linear acoustic wave equation, and the solution for any generic wave that is travelling in any generic direction in the 3D Cartesian system is given by. So, that is the solution where P is the acoustic pressure of the harmonic plane wave. And this acoustic pressure P is given by some amplitude A, whose magnitude can be found based on the boundary conditions in any problem, and then A e to the power j omega t, where omega is the angular frequency, t being the time variable, then plus minus k x x plus minus k y y plus minus k z z, where we also studied about the propagation vector k and the magnitude of this propagation vector, because it is a vector. So, it has a magnitude and a direction. The magnitude is simply the wave number k, which is omega by c. This relationship has been derived, and this gives you the direction of the vector k is same as the direction of the wave front propagation. So, here kx, ky and kz become simply the components of the propagation vector k in the x axis, y axis and z axis respectively. Okay. So, this is the generic equation, and here in all these equations, if we see, if it is a plus sign, which means a backwards propagating wave, and if it is a minus sign, which means it is a wave propagating in the forward direction, which means it is propagating in the positive axis direction, okay, or the forward propagating wave. Okay. So, with this summary, let us start quickly our lecture 6, where we will discuss about two important quantities for wave propagation, which is the sound intensity and the sound power. Then we will also discuss two new types of waves which are very commonly encountered in the problems on mechanical systems. We have the spherical waves and the cylindrical waves. So, what do you mean by sound power? So, at the very beginning when we were introducing sound, so what is sound? It is a form of energy. Okay, and this energy is in the form of the pressure variations or the disturbance or oscillation in the pressures that is transporting through the medium. Okay. So, if it is any propagating or travelling wave, as the disturbance or the acoustic pressure it propagates forward, or as the disturbance or oscillations in the particle they propagate forward in space, what are they doing? They are also transferring the energy from one location to another location in space. So, how is this energy being stored? It is stored in the form of the kinetic energy of these particles, which are set in motion when a sound wave propagates through. So, there is some energy that is propagating through when the sound wave is propagating. So, obviously, then there will be some power associated with it, some intensity associated with it. And just like in other fields, such as in the field of heat, in the field of electricity, you have the same definition for a power and intensity. So, what is power? It is the energy per unit time or the work done per unit time. So, here sound power P, that is the notation we will be using, is defined as the rate at which sound energy is being emitted or it is being reflected, transmitted or received per unit time. So, the rate at which this energy, either depending on the context in which we are measuring it, either emitted, reflected, transmitted or received per unit time, and the SI unit is watts, energy per unit time. It can also be defined as the rate at which the sound energy flows per unit time through a surface that completely encloses the sound source. Now, this particular definition would remind you of the heat flux that we have studied in various other mechanical courses. So, suppose you have some source here and it is emitting. Now, the source is there, it is radiating or it is emitting the energy all throughout in the medium that is surrounding it. So, suppose we had any surface that was enclosing this. Let us draw a surface, a surface that completely encloses this source or this sound source. So, whenever in these lecture series I refer to source, it would mean the sound source. So, over here what you see is that is a source which is like this small ball, it is emitting the energy and you have some kind of surface completely enclosing it. So, it is receiving all the energy that is radiating. Suppose this surface had holes, then some energy would go through, or it was not completely enclosing and it was only partially enclosing, then also in that case not all the energy from the source will be captured, some of the energy will radiate away and it will not be captured entirely by that surface. So, it is important that the surface we are talking about, it completely encloses the source, and then the rate at which that surface will be receiving the energy per unit time will then become the sound power of that source. Now, it is obvious if you think about logically about the sound source, it means that the source is radiating away the energy into the fluid medium or the fluid surrounding it. So, whatever energy it is radiating, we have a fixed source. So, no matter at what distance we measure, it is the same energy and it is flowing per unit time. So, it should not change over space. So, sound power does not change over space, there is no spatial variation. There could, however, be temporal variation, may or may not, depending on how the source is. Source. So, let us say for example, I will take the analogy of a light energy. We had a light bulb, we switch it on and off over time. So, it is radiating the energy into the space, then it stops radiating the light energy, then again it radiates and then stops radiating the light energy depending on how we are switching it on and off. So, over time the energy from that bulb is flowing and changing over time, but not over space. Okay. So, whatever energy is radiating at, suppose some energy is radiating at the time t1 to t2, it should stay the same from one location to another, provided there is no blocking surface or anything. So, the energy should stay the same. In the same way, if suppose we have a noise source or a machinery, now imagine, and we are switching it on, switching it off, then switching that machinery on, again we are switching it off. So, here the source is, the energy from the source is varying over time, or let us say we have got some mixer or some vacuum cleaner, we are changing its speed settings over time, then depending on how fast these machineries are, in general you observe that the sound level rises. So, the more speedy they are in general radiating more energy. So, their emitting of the energy may change over time, or suppose we have a fixed machinery, we are doing nothing with it, just we are running it continuously, then the energy will stay the same. So, depending on how the source is running, the energy may or may not change over time, but this energy should not change over location of the fluid medium. Now, we think about sound intensity. So, it is the energy. So, what was power? It was energy per unit time. Intensity becomes energy per unit time per unit area. and intensity. So, just like sound power becomes a characteristic of the source, not of the location in which it is being measured. So, it depends entirely on how the source is running. Sound intensity becomes a characteristic both of the source and of the location at which it is being measured. So, it is always defined at a certain point, not randomly. We cannot define intensity randomly. We have to specify where exactly we are measuring that intensity. So, it has to be linked to a particular location. We will denote this intensity term by the capital I. It is defined as the rate at which sound energy flows per unit time through a unit surface area that is perpendicular to the direction of wave propagation, or simply sound power per unit area. So, by definition, it should be the surface integral, the power we can obtain by doing the surface integral of intensity with the area over a particular surface that is enclosing the source. So, if you look at this particular equation here, let us just clarify this. So, what does this equation mean? We have got, let us say, some sound source which I am indicating by this red blob. This is our source. Okay. This is the legend for this figure. This means, this red blob means it is the sound source, and then it is radiating away the sound energy, which I will indicate using these arrow like lines, where each of the arrow indicate the direction of the wave propagation. So, the direction in which the energy is flowing outwards from the source. Now, if we had some surface, which I will indicate using this green color, which completely encloses the source. So, no matter what is the shape of that surface, it has to completely enclose the source. So, this is a completely enclosing surface, and what we do is, let us say we take an infinitesimal element here. This is our infinitesimal element, and there would be some intensity. The intensity vector should be in the same direction as the direction of the flow of the energy. So, this is the intensity vector I. Then we have got some area vector which should be normal to the surface area of this infinitesimal element. So, this area vector A is what it is normal to the elemental surface area. We do the dot product, which means we are simply multiplying them, and then we integrate it over the entire surface, then we should be able to get the complete power of the source. So, that is what this equation indicates. So, what should be the unit of sound intensity? Just like power is watts, sound intensity is power per unit area. So, it should be watts per meter square. There is another way to define sound intensity, because here, if you remember, this is the sound wave that is propagating, and how is the energy being stored here? It is in the form of the kinetic energy of these oscillating particles in the medium. As the wave propagates, we have these medium particles, they strike one another and keep propagating the energy from one layer to the adjacent layer and so on, and the wave propagates in space. So, it can also be defined as the rate at which this work is being done by the medium particle on its adjacent particle. So, this will be given by PV. How we are getting this? Let us say we have got some medium particle, it is oscillating back and forth, a layer of medium particles, and they are transferring their energy to the next layer here while striking, and so on and so forth, the energy is propagating. So, the intensity is the power per unit area, and power is work done per unit time. So, what is the work? It should be, the intensity here should be work done per unit time per unit area. So, let us derive this formula. So, the instantaneous intensity at any point would be what? It could be the force being applied by that layer of fluid particle. So, and force multiplied by the distance, and because it is a longitudinal wave, so here the direction in which they are applying the force is the same direction in which the movement is taking place. So, although we do the dot product for f vector and dx vector, ultimately it becomes a because they are both in the same direction, we end up with multiplying their magnitude. So, let us do that. So, that is the work done. Then per unit time, so by dt, and per unit area by ds, the surface area over which the sound wave is propagating. So, this becomes F by, now F by ds would simply become, because it is force per unit area, so it should become pressure, and then dx by dt we are doing. So, we have pressure multiplied by the velocity. Okay. So, that is how we are getting this formula P into V. This is the instantaneous intensity, and it is what? It is the product of the instantaneous acoustic pressure and the instantaneous acoustic particle velocity. Because it is a sound wave, so both the pressure, that is a scalar, as we have already seen here, initially it was a dot product of two vectors because they are in the same direction. It ended up being the multiplication of the magnitude of the two vectors, and P being a scalar quantity, we simply multiply it with the instantaneous acoustic particle velocity. So, this becomes our very first equation, but as you know, what is an acoustic pressure? It is a fluctuating wave. So, the pressure P, it is changing over time. So, which means that at some point the intensity would be high, at some point it will come to a low, and at some point it will become 0. So, the instantaneous intensity should have some fluctuating kind of waveform as well, it should change, which will not make a sense. So, what we do in general is that we take one time period of the wave, and in one time period we try to do a averaging to find out in one complete wave cycle how much intensity we are getting. So, that gives us a more sensible term compared to the instantaneous intensity. So, we get this time averaged intensity. So, in most of the equations and in most of the cases when we sort of discuss or describe the intensity of a sound wave, we in general mean the time averaged intensity, not the instantaneous intensity, because that is a fluctuating quantity. So, this time averaged intensity I is what? You do the time averaging of PV over the time period T. It can also be written in the form of an integral like this. So, integral of P dot V from 0 to capital T, where capital T is the time period of the wave, by 1 by T. Now, if you see here, the magnitude of pressure divided by rho naught C, so P dot V would, so the magnitude of this should be what? It should be P whole square divided by rho naught C, right. So, that means that this is what? This becomes the magnitude of the intensity. So, the intensity is directly proportional to the pressure square, the magnitude of the intensity, and this P is what? It has got a certain amplitude. So, we can directly come to the conclusion that the intensity would be directly proportional to the amplitude square of a acoustic wave. Now, let us see another wave front which is called as the spherical waves, and then we will derive the equation for sound power and intensity for the harmonic plane waves, spherical waves and the cylindrical waves. So, for the harmonic waves, how were they generated? They were generated by some kind of reciprocating flat surface inside a long tube, and the wave front, which is the surface of the constant phase and amplitude, was perpendicular to the direction of the wave propagation, and the amplitude did not change over time. So, there was no attenuation. Now, let us imagine we have a point source, okay, and this point source is radiating uniformly the sound energy in all directions. Now, what do you mean by a point source? Obviously, in the real life we do not have anything that is a point. So, what do you mean by a point source? In acoustics, we will call anything that is a point source if the source's largest dimension is much smaller than the wavelength under consideration. So, let us say we are having a low frequency sound, we are dealing with some phenomenon where we are dealing with low frequencies. So, the lower the frequency, we know that lambda is equal to C by F. So, the lower the frequency, the longer the wavelength. So, if you are dealing with low frequency region, this lambda becomes quite large, and most of the ordinary small kind of objects, they behave like a point source. Whereas, if you are dealing with very high frequency regime, then that same lambda will become small, and then the ordinary objects in centimeters or whatever, they will not behave like a point source. So, we have a point source and it is radiating the waves uniformly in all directions, and here the k vector becomes radially outwards, and the wave front that we are getting, if you see this figure, is a spherical wave front. Okay. Instead of the harmonic plane waves, we are getting a spherical wave front. If you see at any point r, what is the area of the wave front? It is the area of that spherical shell that is surrounding the source. So, the area of that spherical shell is given by 4 pi r square. So, let us see a typical spherical wave. Let us say we have got a small ball and that is pulsating, which means it is expanding in volume, contracting, expanding and contracting, and in that particular, by means of expansion and contraction, it is sort of driving the surrounding medium particles back and forth and is able to create the waves that is radiating uniformly in all the directions. This is the 3D view of this, and this is the kind of wave. If you measure the wave away from the source, what you see here is that it is still a sinusoidal wave as it is going away from the source. So, let us say the source is located, this is the source's line or source's center line. So, as you are moving away from the center line, the wavefront are still sinusoidal in nature, but their amplitude decreases, and this is the contour plot of the acoustic waves. Let us take a snapshot just like we did for harmonic wave. So, we want to observe at a particular instant in time, we took a snapshot. Now, let us say we draw a plane surface perpendicular to the direction of wave propagation. So, we have this. So, do we observe that all the particles, they are in the same phase and have the same amplitude? So, no. So, here the particles are neither in phase nor have same amplitude. Okay. Amplitude is varying because you can see here the wavefront, as you go over distance, it is changing. So, the amplitude here would be higher and the amplitude here would be lower, and the phase as well is different. While one is experiencing a trough, the other one is experiencing a peak. So, this is not a plane wavefront, it is a spherical wavefront. Okay. So, and the direction is radially outwards, wavefront is spherical. Now, what are some spherical waves in the mechanical systems? So, because this course is about noise control in mechanical systems, let us see some common sources. So, at the very first I gave you the definition that if we have a point source which is sort of vibrating uniformly all across its surface and it is radiating outwards, then it becomes like it shows or it gives away the spherical waves. Now, for example, let us say we have a boxed speaker, a speaker inside a cabinet. Here the diaphragm of the speaker is moving back and forth and it is generating a spherical wave. This is a figure from one of the experiments that I did with my doctoral student. In order to get a spherical wave front, how did we create it in the real life? We had a small boxed speaker, we played it in a low frequency regime, less than 500 hertz. Okay. So, in that case the dimensions were extremely small compared to the wavelength, and as the diaphragm was pulsating, the waves were coming out and it was kept more than 1.5 meters away from the ground to avoid the reflections, and we were getting a good spherical wave front. In the same way, there could be various such small sources such as a compressor. So, inside the compressor you have a lot of mechanism, but the outside surface of this closed compressor, it starts to vibrate and it behaves like a pulsating sphere and generates spherical waves. In the same way, you have sparks, or even me speaking here, the voice itself behaves like a point source, the vocals of a human. So, Then we have any kind of small machine resources, all of them will behave as long as this condition is satisfied. So let us solve and find out what should be the solution for a spherical wave. This is our equation to begin with. It holds true for every kind of wave front in a homogeneous medium. So this is the linear acoustic wave equation. Now a spherical wave is typically propagating in the radially outwards direction. It is not propagating like in the particular x direction, y direction or z direction. Let us say we have a source somewhere at the origin and we sort of plot the sound waves. We can think of them as waves that are propagating along some radial direction. So it makes sense to then derive the equation in the spherical coordinate system. So this is our spherical coordinate system. Okay, r, theta and phi, r being the radial vector where we are trying to make the measurement of the acoustic pressure. Phi is the azimuthal angle, which means that if you project this point onto the xy plane, the angle that it makes with the positive x axis becomes your phi, and theta is like the elevation angle. So how it is measured? You draw this radial vector and see what's the angle it is making with the positive z axis. So you get these, and this is how you represent them in the spherical coordinate system. So the same equation in the spherical coordinate, Laplace square is given by del square by del r square, 2 by r, del by del r, and this kind of complicated term having theta and phi all around. But the waves are spherically symmetrical. See, all of this, they should be spherically symmetrical, which means that if suppose we have this sound wave, it is radiating, so it is a spherically symmetrical. So what is here in one point, it should be the same in the other point. It should be independent of theta and phi. It should only depend upon the radial distance from the source. So for that uniform spherical wavefront, which is symmetrical, so this del by del theta and del by del phi should be 0, because it does not change with theta and phi, the pressure. So hence these terms are automatically neglected, and we end up with nabla square being this particular term. Okay. So they behave like, as I said, they behave like some kind of sinusoidal waves that are propagating along the radial direction. So why not we start with and represent the pressure in the form of whatever. So I told you in the very beginning when we were studying about like harmonic plane waves, why we study them, because once we know this basic solution, we can solve complex waves and various kind of complex waveforms as superposition of harmonic waves or changing harmonic waves. So here also we will begin with the solution as a harmonic plane wave. We will think that it is some kind of a harmonic plane wave, but because the amplitude is changing with distance, so here this amplitude, instead of being like a constant term, here it is AR, which is a function of the radial distance r. So we represent it, and the direction of wave propagation is this r vector. So now let us see what this AR is. So suppose we have a source at the origin and we are measuring its power or intensity at any point r. We know that the intensity at r should be powered by the surface area over which it is being measured. Here we have taken a sphere, so the surface area becomes 4 pi r square. So this intensity is inversely proportional to r square, and because the intensity is directly proportional to the amplitude square, so the amplitude becomes inversely proportional to the radius. So now we have come to know that this is a term which is inversely proportional to r. So this AR, which was a function of the radial distance, is now A by r, where A becomes some constant term, which is determined by the boundary conditions or the problem at hand. So this becomes our final expression of a spherical harmonic wave equation. Fine. So the sound intensity, let us derive that. These are the equations we have already seen. Using these equations, we are going to come at sound intensity. So P into V, or the averaging of P dot V over time. So let us start with the sound intensity of harmonic plane wave first. Let us consider a plane wave travelling in x direction. If we see, this becomes the equation, this becomes the velocity equation, which is represented by P by rho naught c in terms of its magnitude. Then we add the plus minus signs based on whatever is the direction of wave propagation. So if you multiply the two things together, you end up with this term, from here and here. So, which means that the intensity is simply some, the magnitude of the intensity is p square by rho naught c. This is how it is represented. So, it depends on the properties of the cosine waves. We will not go in detail of this. So, p max square by 2 rho naught c or p RMS by rho naught c. And for a spherical wave also the same equation holds true, and we end up with the same equation, which is p max square by 2 times of rho naught c, which is p RMS square by rho naught c. Now, these equations you have to just remember them if you want to be in the field of acoustics or noise control, because it is going to be used in a lot of ways. Now, the last kind of waves which we will discuss in this course is the cylindrical waves. And depending, see, the wave front that is being generated depends on what source we are sort of taking into consideration. Like for example, with the spherical waves, it was a point source that is uniformly radiating throughout in all the directions. So, which means that the vibration velocity stays constant over the surface of that point source. Suppose you have got some kind of line source and it is vibrating uniformly, then you generate a cylindrical wave front. So, this is a line source, okay, and the wave front at any distance would then become a right cylinder or a right circular cylinder, and its axis would be same as the axis of the source. So, again the direction of the wave propagation is radially outwards from that source line, and the area of wave front at any particular distance becomes the surface area of this cylinder, which is the circumference of the circle multiplied by the length of the source. So, it is 2 pi RL. Some of the examples of cylindrical waves in mechanical systems, we have pipe and duct systems, So, here it is the emission by, it is not the emission, the noise inside. So, that is the distinction I want to make, because when we were discussing about harmonic plane waves, we saw that if inside the pipes we have some reciprocating motion that is generating sound waves. For example, inside the tailpipe of a vehicle, we had the piston of the engine that is pushing the sound waves through the tailpipe, then that becomes inside the pipe it behaves like a harmonic plane wave, and as it emits outside into an infinite baffle or atmosphere, it becomes a point source. So, it emits a spherical wave. Okay. So, this is not that, it is the waves that are created. So, suppose some kind of fluid was flowing through this pipe here, and because of the flow of the fluid inside these pipe and ducts, the surface of the pipe starts to vibrate. So, it is not the waves flowing inside it, but rather because of the flow inside, the surface of the pipe is vibrating, and that pipe surface, when it starts to vibrate back and forth, it behaves like a line source which creates the cylindrical waves. In the same way, submarines, jet engine exhaust, by the means of how the way they are sort of having the fluid flow go, over here they are creating these harmonic waves. To make it more clear, this is not harmonic, this is, they are creating the harmonic waves in the surrounding atmosphere, where they are behaving like a line source. Okay. So, I hope this makes the distinction clear between or the confusion between whether the pipe or a duct has a harmonic plane wave front or a cylindrical wave front. Inside, if it is a reciprocating motion that is pushing the fluid inside, then it becomes a harmonic wave front, but by the virtue of the flow, if it is able to generate the structural vibrations in the pipe itself, then outside it radiates a cylindrical wave front. Similarly, the uniform traffic flow on a straight road generates this, high speed trains generate cylindrical waves. So, what happens? So, suppose there is some line source and we are giving a side view of it, and we take two microphones at two separate distance and measure the pressure. So, there should not just be a phase shift, but there should also be a change in the amplitude, and this P RMS. So, just like a spherical wave front, here the intensity is decreasing and hence the amplitude is also decreasing with time. Okay. To obtain the cylindrical wave equation, we are applying this acoustic wave equation in the cylindrical coordinate system, okay, where any point P where we want to measure the sound pressure is given in terms of r, theta and z. R is where r is the, if you project this point onto the xy plane, the distance in the xy plane becomes r. The angle that this projection makes with the x axis becomes theta and z becomes the z coordinate. Okay. So, that is how you represent it. Now, if you solve it, which is not within the course of this because it is still a beginner's course in noise control and mechanical system. So, we will not go into the derivation, but we directly come to the solution of this particular equation. It is slightly more complicated. We get some amplitude which was a function of the radius, but how it is a function of the radius? It is the Henkel's function of second order multiplied by some constant into k times of r, then e to the power j omega t, which is a time varying sinusoidal signal. Now, let us see how the pressure is varying with the radius. I told you here that as you move away your microphone, the amplitude should change. How does it change? Let us see the sort of function. So, at any point P, suppose we measure it. So, what should the wavefront be at any point P? This should be I at this point should be P by the area of the wavefront over which you are measuring your power. So, the sound power divided by the surface area. So, this should give you P by 2 pi R L, that is the area of the wavefront. So, ultimately it comes out to be here I R is P by 2 pi R L. So, which means the intensity is inversely proportional to R. So, in the spherical waves we had inversely proportional to R square. We also call it as the inverse square law for the spherical waves. In the cylindrical it is just inversely proportional to R. So, the pressure is actually inversely proportional to root of R. That is how the variation happens, and the intensity of this cylindrical wave is given by P square AS or PAS whole square divided by 2 rho naught C. Here PAS is the asymptotic amplitude, which is this constant here. Okay, fine. So, before we end this lecture, just a small conclusion of all this exercise is that, see, suppose you have a source which is emitting spherical wavefront. That means that with the distance the attenuation is automatically happening. It is attenuating at the pressure is attenuating at the rate of inversely proportional to R square. If you have a cylindrical wave, it is inversely proportional to R, and if it is a harmonic wave, there is no attenuation at all. So, if in some ideal situation in a machinery setup, we have some source that is spherical, there is another source that is cylindrical, and then there is another source that is harmonic plane wave or harmonic plane source. The harmonic plane source is more dangerous. Why? Because there is no attenuation, no matter how far away you are. So, that takes a priority over cylindrical and spherical sources. A spherical source will automatically attenuate over space or distance, and same goes with the cylindrical. So, the attenuation wise, you can say the rate of attenuation of spherical is larger than the rate of attenuation of the cylindrical spherical source, cylindrical source, which is larger than the rate of attenuation of plane source. So, plane source takes our priority because there is no attenuation at all, whereas in the spherical you automatically are getting the attenuation. And one concept that can be used in various machineries is, by some means, if you can convert a plane source into a spherical source, then automatically you get an attenuation. Okay. With this, I would like to end this lecture, and thank you for listening.